Then welcome for today's exercise in electrical engineering. I'm here in the room with, I don't know, maybe 8 to 10 students. I think it's only 8. And my name is still Matthias Magdowski. I'm a confident complex number calculator at the Otto von Guericke University of Magdeburg in Germany. And I will share my screen in a second. So according to our exercise table, the idea for today would be to discuss the tasks 26 and 27. And there are some more people joining the room. And I've already opened up the exercise booklet. So here is this task 26. It's on complex phasor calculations. And maybe I will switch over to the hand tool and maybe zoom in a bit more. And what I can say is that there's already a quite nice solution from last year, where I think I'm wearing exactly the same center hat together with Francesco, where we discussed this and where we also did some calculations in Octave. So the idea for today would be maybe if you agree to kind of repeat these calculations, maybe in Python, and maybe also do some sketch. So the task, and you can see it's just a one-star task, should not be too complicated. It is actually not too complicated. We have given a sinusoidal time function or cosinusoidal time function, and it's a voltage as a function of time. So how would you call, or how would we call this term here? This is the amplitude, exactly. So how would you call this? What is the? Yeah, this is the frequency. This is a special kind of frequency. It's the angular frequency. It's 2 times pi times f, the usual frequency. This is the time. It's a function of time. And how would we call this here? It's a phase shift. And phase shift more or less only makes sense if you have more than one time function, because what else should you compare phase with if you don't have a second time function, or if you have a precise time reference somewhere? Okay, so we have a time function. This has some amplitude, some angular frequency. It depends on time. It has a phase shift, and this is really some real valued time function. Why I explicitly state this, because this is what people often confuse, and you will confuse it as well. Yeah? So this is a time function. There's nothing complex in there, no complex phasor, and it really depends on time. So it's a function of time, a voltage as a function of time, and we can insert different time steps, and then for different time steps we get the value of this time function. Okay, so it's nice. It's also something that we could measure, take some oscilloscope, plug it to, I don't know, our power mains outlet here to the power socket, and then we would also measure something sinusoidally or cosinusoidally changing over time. Okay, and so now we should convert this into a phasor in exponential, trigonometric, and Cartesian form. And yeah, this is maybe what we can quickly discuss, and then we can see how we can calculate this. So I've not opened up my drawing program yet, so I will open up my drawing program, which is not Outlook, but Journal. And there it is. And paste this into my drawing program. And yeah, maybe also paste the rest here. So we would like to have this exponential, trigonometric, and Cartesian form. So how do we get the exponential form of our phasor, and how would you write this? Any ideas? What have you learned in the lecture before?
So this would be 5e power.
Yeah, it should be the same amplitude. We can discuss if it's really the same amplitude, okay, but we will take the same amplitude, then times e to the power.
By 60.
Yeah, and then the imaginary unit, and because, so this is Euler's number, or Euler's constant, 2.72 something. And this is the imaginary unit. And the imaginary unit in mathematics is called I. But what problem do we have in electrical engineering? It's the same symbol as for the current. That's why we usually write a small j. I try to make this I into a j, and then we give it the same phase in degree 60 degree. So this would be our complex phasor. This is now really a complex number because there is this imaginary unit in there, and it's not a function of time anymore. So we would usually call this also V because it's a voltage phasor, and with some underscore to denote that it's a complex number. And the complex number in this exponential form is given in terms of the amplitude or the magnitude of this complex number, which is the 5 volt, and the phase shift, which is the 60 degree. And that's nice. So you can think of this as Professor Fick told, as kind of a vector. So it's not a vector, it's a complex number, but it's a bit like a vector because a vector also has a length, which is the amplitude here or the magnitude, and a vector also might have some direction. So if we draw it in a complex plane, and this would be our real axis, and this would be our imaginary axis, then we always count angles from the positive real axis and then counterclockwise. So 60 degree might be something like this, and I'm not good here. I don't have a scale to check how long 5 volts or 5 units are, but this should be the 60 degree, and the length of this should be the 5 volt. So imagine this phasor is really something like an arrow in the complex plane that has a certain length, which is the magnitude, and that has a certain angle. And the angle is set counterclockwise from the positive real axis. What is the difference to a vector? Why it's not a vector? It's looking like a vector. Say again? Yeah, the thing is, a vector is really something like a direction with a physical meaning, and you can add vectors. There's a vector sum, and you can have a scalar product with vectors, and you can have a product with a vector and a scalar number. But for example, there is no vector division. But for complex numbers, there is a division. You can divide complex numbers, one number by another complex number. And that's the difference to vectors. So as said, it's somehow similar to vectors, but from a mathematical point of view, it's not the same because we don't have a vector division, but we would have a division. We can divide one complex number by another complex number. That's kind of a difference. Okay. So that's the exponential form. So now, what does this trigonometric form mean? Anyone some idea? There's a very basic equation that e to j phi or e to j alpha can be also rewritten as
cosine of
exactly cosine alpha plus j sine alpha. And if we just take this and insert this into our equation, then I will continue in green. Then we get this trigonometric form, which is 5 volt. And then I maybe need to have some brackets to say it's the cosine of 60 degree plus j the imaginary unit multiplied with the sine of 60 degree. And then of course we could calculate this and say it's 5 volt times the cosine of 60 degree plus j times 5 volt times the sine of 60 degree. Okay, so this is our trigonometric form. To be honest, no one really needs this trigonometric form in this way. It's because it's kind of lost in translation. It's somewhere between this exponential form and the Cartesian form that we would like to have. So what is the Cartesian form at the end? Yeah, just this calculated. So we take this, calculate this, and we get some number, and we take this and calculate this and get some number, and then we have the one number plus j times the other number. And so now this is something that we would need to calculate. You can calculate it if you like using a classical calculator. I won't use a calculator. I have forgotten my calculator today. And you can also calculate this with a calculator. I think cosine of 60 is easy because cosine of 60 is 1 over 2, and 5 volt times 1 over 2 is 2.5 volt. And yeah, sine of 60 is more complicated and times 5 volt. No one can calculate this in your head, but the thing is, where do we find these numbers in the nice schematic that I have drawn? So let's give this some more names here. This is the magnitude. And this is the phase of the complex number. And what we get here at the bottom, this is what we call real part. And the one that we get here, this number, has anyone calculated this number so far? Say again? Root 3 over 2, maybe, and then times the 5 volt. But we want to be, say again? 4.3. This is nice. 4.3, and then the unit is volt. There is this mathematical joke, you know. I usually do this in my mathematics preparatory class. Also doing conversion between Cartesian coordinates and spherical coordinates. And so the story is a bit that there's some airplane is lost somewhere and it's very foggy and there's only very few fuel left in the tank of the airplane, and the pilot really needs to land the airplane soon. And the tower has some radar, and the tower can determine that the airplane is in a certain distance in this direction and in this direction and to the top. Yeah? And from this, you can calculate by the Pythagorean theorem. You could calculate also that the distance is, I don't know, the square root of 37 kilometers. Yeah? And then, of course, if you answer this to the pilot, yeah, you are just the square root of 37 kilometers away from the airport, you can land soon. Then, of course, it's from a mathematical point of view, perfectly exact answer, but it won't help you too much. Yeah? And so we are engineers, we are not mathematicians. We are, at the end, we are interested in floating. In most cases, we are interested in these floating point numbers. Okay, so this is what we would call the imaginary. I really have to be careful here that my my letters are readable. Imaginary part. Do I have enough space? No, I will write the part here. Okay. So real part and imaginary part, magnitude and phase in the exponential form, and real and imaginary part in the Cartesian form. Where do I, in this schematic here, find the real part and the imaginary part?
On RE?
Yeah, on this axis here, or the vertical distance is?
The real part.
No.
Imaginary.
Yeah, this is the real part. This is like the real part of our complex voltage phasor. This is the imaginary part of our complex voltage phasor, and the 5 volt here that we have written on top this would be the magnitude of our complex voltage phasor, the 5 volts. And yeah, the 60 degree is like the phase, right? The phi here on top. This is the small Greek letter phi. And that's more or less it. So maybe, I don't know, think about this like some vector. As said, from a mathematical point, it's not a vector, but it has a certain length, it has a certain angle, and we can split it up into components which are like the real part and the imaginary part, like some x and y component of a vector. And the conversions, as you can see, are pretty similar. So if we have magnitude and phase, we can calculate the real part and we can calculate the imaginary part. How could we go back from real part and imaginary part to magnitude and phase? If we have the 2.5 volts as a real part and the 4.3 volts as the imaginary part, how would we go back to magnitude?
Square root.
Yeah, square root of these components. So maybe I will write this in gray. So if we want to have the magnitude of our phasor, it's the square root of the real part of the complex phasor squared plus the imaginary part of our complex voltage phasor squared. And how do we get the phi, the angle? Think about trigonometric functions in this triangle, because this is a right angle triangle. And we want to have this angle here. Say again?
Arctangent?
Yeah, tangent or tangent, because it's the the length that is opposite to this angle divided by the length that is closer to this angle. And I will write it like this, that I say the tangent of this angle is the ratio between the imaginary part of our complex phasor divided by the real part of this complex phasor. And then the inverse, of course, would be the Arcus tangent function. Okay, this is more or less, let's say, what you need to remember when dealing with these complex numbers. Now, one question that you might ask yourself, and if you have questions in between, feel free to ask all these questions. Yeah, but one question that I would have as a student looking at this is, why do we need these different forms? Would this also have been your question? No. It's more like a general why. Okay, no. I would ask myself, why do we need to have these different forms? Why it's useful to have an exponential form? Why it's useful to have a Cartesian form? And okay, no one really needs this trigonometric form. It's, as said, it's somewhere lost in translation. It's just what is in between the two. But why do we need to have these different forms? Someone an idea? Why do we need to convert complex numbers between this exponential form and the Cartesian form back and forth? There's an idea.
Isn't it easier to calculate multiply imaginary numbers with the Cartesian form, and it's easier to add them if they're in the exponential form?
Yeah, so exactly the opposite. So it's much easier to do plus and minus in the Cartesian form, because plus and minus is just the sum of the real parts, the sum of the imaginary parts. And it's way easier to do multiplication and power and roots and square roots and division in this exponential form. And that's why we need to have these two different forms. At the end, to be honest, if you use a calculator, if you use MATLAB, if you use Octave, if you use Python, you do not really care about this, because these tools in the background will do all the conversion for you. Still, sometimes we will see, okay, LTspice will output, for example, always magnitude and phase, and sometimes we would like to have the Cartesian form. yeah, so, and then you might need to do the conversion yourself, or you might to have a good idea how maybe I can trick the program into doing the conversion for you. Okay, which questions do you have so far? More questions? No questions? So then we could at first check, okay, what we have done now is we've converted this time function into phasor form, we have calculated its different forms, and we have drawn the phasor on the complex plane, and we could check maybe if my mouse wakes up once again, go to the result check, go to the task 26. Okay, there's no sample solution here. Yeah, okay, so but let's assume that what we have done is correct, and now of course we can do a check. Yeah? So I will go back to this task and go back to my sheet here, and as discussed before, the idea would now be to do this in some kind of numerical tool. In the video from last year here, we have done it in Octave. So this year, let's do it in Python. Yeah, so go back to this, open up my Python that I already have here. I'm just using the plain Python shell. Of course, you could also use the Jupyter Notebook or whatnot, but this is easier on my computer. And so the advertisements of slogan of the Python programming language is a bit that batteries are included. Yeah, so that there are already lots of functions built in. But if you check, for example, there is no P defined. And there is, I think, also not even a cosine or sine function defined in the Python language. So you always need to have a library for this. And this one is called numerical Python, NumPy. So we will import NumPy, and NumPy is a bit long to spell, as a shorter command, which I call np. Okay, so this worked because it's installed on my computer. And now we can maybe insert our v-phasor, our complex phasor, as it's written here. Magnitude times the exponential function multiplied with with the phase of the argument. So of course Python won't care about units, so I just write 5. And then yeah, we can check there is no exponential function defined. Yeah, but it's within this NumPy package. So if I write np(x), there is some exponential function that would hopefully do the job for us. Then I think there is no j, but there is some, I think there's some 1j. 1j is always the imaginary unit. And then I write 1j times 60. Let's check if it works. We have already calculated it by hand, right? We would expect that we get this result here, 2.5 plus j times 4.3. And Python is always omitting the result. So, but there we see the result. And as you can see, we get more something like minus 4.7 minus 1.5 times j. This is the well-known garbage in, garbage out principle that I maybe explained last time or the week before. All these computer tools, they are very, very powerful, but you need to know how to use them. And the problem is often, like today, sitting in front of the computer. The computer will always calculate right, but you have to use it properly. So has anyone an idea why this calculation is not working? Have you used computer tools before? Have you used your calculator? What is important if you do calculations with angles in your calculator? Set the calculator to if the angle is given in degree or in radians. And these computer tools in most cases expect radians. So the question is, how do I convert from degree into radians? Yeah, divide by 180 and then multiply with p. Because then the degree and the degree, they will cancel each other, and we multiply with the p radians. So we get radians. Okay, so let's check. Then, yeah, as said, there is no p or pi defined. So I need to write np.p. And then it calculated something, and then I can output the result once again. And then we see, oh, this is looking nice because we get, if I make this window a bit smaller, so that we can see also the other result before. So then we get 2.5000 with some 4 at the end. Why do we get the 4 at the end?
Because pi is irrational.
Yeah, because pi is irrational and there's just a limited accuracy, and this is just the rounding error, let's say, of the computer. And then we have the 4.33 for the imaginary part. Okay, so this is looking perfectly nice. So now if we would like to have the real part and the imaginary part out of this number, how could we get this? There are just functions that are called real, np real of our v phasor. This will give us the real part, and np imaginary, or abbreviated imag, will give us the imaginary part. And yeah, so the phasor or the output here is always in this Cartesian form once again. So how would I get the magnitude of this phasor?
Sum of the square sum.
Yeah, this is of course what I could do. So I could take the real part, copy it, square it, take the imaginary part, add it, square the imaginary part, and then take the square root of this. Oops, and I think there is no square root defined, so there might be an error message. Yeah, square root is not known, so I have to write np square root, and then we will get the square root. Why does it not work? np sqrt, not supported for the input type. Okay, so I'm not super familiar with Python. I don't know why this not work, but you can see now things are getting complicated. There should be an easier way to do this. Does anyone know an easier? Can anyone imagine an easier way? This is also a set called the magnitude of this phasor. So magnitude in English is also known as the magnitude of another number, of some also negative integer number or a negative number, is the absolute value. Yeah, and so if we say np abs of our complex voltage phasor, then we get 5. We get back our 5 volts here. And how do we get back our phase? Yeah, we could do it with this arctank or arctangent. Probably I also need to use np. I'm not sure if this will work because I don't know why the other thing here did not work before. So take the imaginary part, divide by the real part, and then take the arcus tangent, and this says there is no A10 function, so I don't know, maybe it's called like this, and this works. So why don't we get 60? Because this is in radians, so what I need to do to convert this into degree? Yeah, divide by p so that the radians will cancel, and then multiply with 180, and then once again, yeah, this is the reason why I don't like Python, to be honest. Then we get the 60. Yeah, and there should be also an easier way, and the easier way is to say, okay, we take the angle of our complex voltage phasor, and okay, angle is also not defined because I need to add the NP angle, and there's the angle, and then if we take the angle, multiply with 180, divide by p, then we also get it in degree, if you don't forget about the NPP. Okay, there it is. And then you can see, okay, kind of a slightly different function, different rounding errors. We don't get exactly back to 60, but to 59.999. Okay, but this somehow works. And so we have done the conversion back and forth. And what we might also would like to do is to draw this phasor diagram also in Python. And there is some function that I have opened up in my browser before, which is called arrow. So there is some library, and maybe I can switch to the stable version. Yeah, I don't know. So in some other library called matplotlib and pyplot, there's some function that is called arrow that will draw an arrow, not an arrow, but an arrow. It's kind of discouraged to use this, obviously, or to be honest, I did not get the other function running, so we will use it anyhow, but it works in a way that you give starting coordinates, you give some delta, and then you give some arguments. So let's check it out if this works. So we will import this library, import matplotlib pyplot, which is also very long as the shorter PLT, and then say inside this PLT there is this function that is called arrow, and we want to have the arrow starting in the origin of our coordinate system at 0.0, and then the x coordinate, let's say, should be the real part of our complex voltage phasor, and the y component should be the imaginary part of our complex voltage phasor. And okay, and then I forgot the closing bracket, and then okay, it once again says this is not defined. This is really, if you are more used to Octave, then this is super annoying. Okay, and then it created some object, and with PLT show we can show this, and then there is this arrow. I don't know why the arrow did not get a tip at the top, but it's pointing from 0.0 to this. Yeah, and so now with some arguments inside this function here, so if I close this, I can get back to the command line. Now there would be some functions where we can say that we might want to have a head width. And I think there are not that many more arguments. We can give a color, and there was some command that I don't find right now. I will maybe open up my sample solution that I prepared in advance. Find it on my computer quickly. So there it's somewhere hidden in my many folders. No, not LTspice, but Python, and update this. Yeah, and so here I have some command, because at the end this is what we need to equal the axis and maybe add some plot. So I will just copy this part here. To the script. Yeah, because the problem with our plot is that the axes are not equal. So if we try it like this, once again, just copy this. So this should be the voltage phasor real part dot real, and this should be the voltage phasor imaginary part. And now I've said this is a phasor, it should be in green, and we should plot this. Okay, then once again I can say plot and show with some parentheses, and now the arrow has got some head. But the problem is that this axis is still longer than the other axis, and that's why the angle is not working, right? It's not really the 60 degree, and the 60 degree depends on, do I make this longer or smaller? And this is done by some more comments that, yeah, as you can see, I also don't really remember. So let's just copy them from whatever I've prepared here. So we can label the axis, say there's a real part, there's an imaginary part. We would like to have a grid, and we would like to make the axis equal, and maybe also show this legend, and then plot, and then I hope it works. No, it does not work because, yeah. As you see, I'm not super I'm not super experienced with Python, and it's not that in this way it's not that handy as okay, and there my phasor is. So this worked, and now if we compare it with the schematic that we have drawn before, it does not look too bad, right? So we have the same 60 degree angle, we have a real part. You can check this lower right corner here, so that the real part is exactly at 2.5 something and the imaginary part is at 4.3, which nicely makes sense. So this way we can draw phasors in such a plot in Python. Okay, then which questions do you have so far? Then what we can also try is to also kind of solve this task in LTspice. So I've opened up LTspice. I will open up a new schematic, and now I need to have, I want to have a voltage. So how do I get a voltage? Which component will give me a voltage? A voltage source. So let's go to component and find a voltage source, which is here. So I can place a voltage source. Then, yeah, it probably would not be a too bad idea to really have a current flowing somewhere. So I will just take a plain resistor, place it somewhere so that the current source can supply this resistor with the voltage that we would like to have. Put all stuff together. You remember from last time that we always need to have a ground node in our circuit. And now if you check this lower left corner here, you can see that this node is once again automatically numbered. It's 0, 0, 1. So I will give this node a number and call this phasor, maybe just voltage or voltage phasor, I don't know. Call it whatever you want, just that we have a fixed name. Put this there, connect it together. So now this node is the node that is called V phasor. Okay, so then the resistor need to have some value. I will just give it 1 ohm. And now this voltage source is not a DC voltage source. It should be a complex phasor voltage source. So I go to advanced, and here we can set AC magnitude or amplitude and AC phase. The amplitude in our task is was 5 volt, and the phase is 60. Unfortunately, it's nowhere really given here that the phase should be in degree, but it is, as we might see later on. So there we have AC 5 volts 50 degree. Now I can simulate, and what we want to do first is maybe do this AC analysis, do the calculation for different frequencies. The frequency at the moment does not really matter, so I will just say we want to have a list of frequencies, and I will do it for 1 Hertz. Okay, and then we get the result, and we can see, okay, our voltage at this phasor, or the voltage phasor of our source voltage is 5 volt. Here, the angle is given 60 degrees. Okay, what we would like to have is this as real part and imaginary part. Unfortunately, there's no way to do this here, but we can do a cheap trick. And the cheap trick is we will not just calculate one frequency, but a second frequency and maybe a third frequency, just 2 and 3 hertz. And now if we do the calculation again, not this table is opening up that we have seen before, but some schematic. And now we can plot our voltage here once again. And now we see, okay, how this voltage changes with frequency, and it does not really change. And we see this here scaled in decibel. Remember that maybe in the very first exercise you did something with decibel calculation? Yeah, so it's not really meaningful, but now if you click with the other mouse button on this and change the view, we can change it from this Bode representation to what is called a Nyquist diagram. And the Nyquist diagram is like a complex plane. This is the imaginary part, this is the real part. And as everything is just one point and no line, nothing is drawn, but if you click on this, you get like a marker, and now we can check that the real part, so the marker is here, that the real part is quite precisely at 2.5 volts and the imaginary part is at 4.33. So this would do the same kind of calculation and conversion. In with complex phasors in frequency domain. And there would also be another way to do this. So for this, I will copy this. So there's the copy tool. Then open up a new schematic, paste this into the new schematic, maybe enlarge this, and change the source from this AC source to a real time domain source. And for this time domain source, I will use a sinusoidal voltage. And once again, what was the magnitude? 5 volts. And the phase shift was 60 degrees. Here is also given that it's 60 degrees. And I will give it, I don't know, some kind of frequency. Once again, maybe 1 hertz, 1 full oscillation per second, and say OK. And so now we have this description here for the source. And our simulation command is still in frequency domain. So I need to change this, go from AC analysis to transient analysis. And now the trick is maybe also a bit weird. So we have set here 1 hertz of frequency. So the periodic time is also 1 second. And what we want to have in our calculation to go from the exponential form to the real part and imaginary part is we want to have the cosine of this and we want to have the sine of this. And yeah, we are giving here, we have given a sine function. So if we, let's calculate it for 1 second, then we should see 1 full cycle. So if I plot this, now we see 1 full cycle. And inside the cycle is of course the sine of our 5 volt and 60 degree phase shift. And where is the cosine in this schematic? Think about the trigonometric functions. Shifted by 90 degrees. And so this axis here is in seconds. Where should I find the 90 degree? So this is 1 full cycle. The 1 full cycle is how many degree? 2 pi in 2 pi radians or 360 degree. So where's 90? 0.25 seconds. So here, somewhere here, yeah, and you can see. So this is our imaginary part. This is the 4.33. And here's our, at 2.5, this is our real part, the 2.5 volts. And so then if we, as said, it's a kind of a strange way of calculation, but it works. If we just go to 1/3 of the full period, it's 90 degree of the full 360, and recalculate. Yeah, and so now if I use once again some marker, the marker window is always hidden behind my camera window. If we move the marker to this position, here at the very beginning, there's my marker now. You can see this is our imaginary part, the sine function term. 5 volt times sine of 60 degree. And if I move the marker all the way to the other side, to the end, now the marker is here. Yeah, it's the 90 degree phase shifted sine, which is a cosine function, and this is the real part of our complex number. So yeah, at the end, we've done this, we've talked about this a little bit in equations, we have done this calculation and plotting in Python that somehow worked with lots of Python programming mistakes from my side in between. And then we have done these 2 ways of calculating this in LTspice with some real calculation in the frequency domain and some transient simulation.